All right, I believe the rest of these slides are about just kind of cleanup about where caches are used otherwise. We've talked about using caches inside of the data cache. There are actually many locations that you can use caching, and there's even caches outside of hardware that are used. You've probably heard of web cache with like Hibernate and whatnot, and they use a type of cache mentality. Let's go through a couple other choices. What about instructions? We've talked about data caching, where you do loads and stores. Can you cache the instructions? Well, can you? Yes. Should you? It actually turns out you can just treat them as normal data and allocate the cache lines when fetched. You can usually you create a second cache called an instruction cache or an iCache, which caches instructions only. How do you know what type of cache to use? Should it be direct map? Should you use a large block size or a small block size? Actually, that's the best question. What should be the block size in an instruction cache?
7.
Should it be big or small?
I would think you can make it big and it wouldn't matter because you're going pretty much synchronous.
Yeah, you want it to be big because that would help you avoid what type of misses? The compulsory, because usually your instructions are one after another, right? So when you bring one instruction, the chance of using the one right after it are pretty high. So you want your block size to be very big in your instruction cache. Advantage of a separate iCache, why wouldn't you want to share this with your data cache?
Because your instruction cache is not going to be written to, where your
Right.
data cache is.
It should never be written to.
Okay.
If you're writing to your instruction cache, you are writing self-modifying code, which is only going to end poorly. So yeah, what could go wrong with all this? Well, yeah, if you start modifying the iCache or something like that, you now need to somehow keep the two in sync, and that'd be somewhat problematic. But people don't write to their iCache or to their instruction memory, or at least I hope y'all don't. You?
Mm-hmm.
You do all the time?
Mm-hmm.
Wow, nice. All right, how do you cache, put it into the pipeline? Replace instruction memory iCache, data memory dcache. Memory is now at variable latency. Both caches can be missed at any time. So back with our pipeline, this hopefully looks somewhat familiar. Your memory, now you have a data cache, which then connects to memory, and of course over here you have iCache, which again connects to memory. The hopes of this is that dcache, you can speed up your pipeline because your dcache is going to be faster, as well as your iCache. The issue is that if it misses the dcache, you now just have to stall your entire pipeline until memory comes back. So there's again, in general, cache is SRAM, main memory is DRAM, disk is magnetic media, or nowadays solid state drives. Cost per unit is high up here, access is fast, latency is low, but that's why they're small, and then up here is big. This gigabyte should be replaced with terabytes now. It's too expensive to buy in terabytes. Yet we want to, other problems I'm saying, DRAM's too expensive to have terabytes of, but we want our programs to work even though they require more storage than we bought. So what we do, we usually have a program that uses the hard disk as a point of memory, and this is where virtual memory comes, well, it's where different ideas come into. So you can have this problem of not enough memory, leave it up to the programmer. When you run out of memory, you need to go fix it yourself, which generally involves writing, the programmer has to write stuff to the disk and then read it out later. This in general is not always the accepted way of doing it, although it's not a bad solution in certain domains. All your game consoles, that's what they do. The game does it itself. And the reason for that is they're trying to eke out as much performance as possible. Cell phones, you usually do this too because they're usually in a low power environment. They don't want the operating system doing certain things. So doing it this way is not a bad idea for certain situations. But in general, you don't want the programmer to be doing it. You want to give them some facilities to use. Solution 2, which is not used nowadays, something called overlays. You basically, it's performed by the compiler, and it's going to determine overlay regions, and so it adds code to your code that if you're doing some region of memory, you know to go ahead and look out to see if some other process is using it. So for example, you might have the dark green program, the tan program. Oh, I'm sorry, I did that wrong. Each column is a program. So you have 3 programs, and each of the memories that they're using is what's colored. So you would know that if you're using the purple memory, you may have to check with other programs. Notice that program 3 only uses purple, program 1 uses all of them, and program 2 uses green and the
What if
purple.
your processor is colorblind?
Then we're in deep trouble. The idea here is that the compiler is going to inject code into your program to kind of automate the switching out of main memory, memory to disk. All right, but that's not what we do. Nowadays we do something called virtual memory, where we add a piece of hardware and software that automatically translates every reference you have from the virtual address of your program to a physical address that actually exists in your machine. So for example, your virtual address may be 800, and then that might map to 3C00. Whenever you see the word virtual, that just means a level of indirection, aka virtual address gets changed into a physical address. Let's see if we get another good picture of why we're doing this. Or it could be in the disk as well. But you don't care because you're the programmer. The operating system and the hardware take care of this for you. So the programmer can see a memory array larger than the actual DRAM with virtual addresses. And it allows virtual memory to share the physical memory without knowing other programs and without worrying about one program modifying another. So this is protection. Okay, what is this doing? Let's say you have process P1 and process P2, and then your main memory is something like this. Using this hardware, you might have this piece of data going right here in main memory, maybe this piece of data going over here, maybe we'll have this one going right down here, and then this last section going down here. And then maybe for some reason, this part has to go to your disk. That's kind of a disk. Okay? It's a level of indirection so that your program sees memory like this, but in reality it's being translated to something else. Maybe it's a different piece of memory, or maybe it's somewhere on the disk. And so you write your program, you just program it, the compiler gives you your memory addresses, and you can just run it, and then your hardware later will translate it to where it needs to go. Because the operating system can then, when it loads your program, say, okay, I have memory available right here, I'll just map your piece here over to that piece over here that is available. Y'all see the point of this? Somewhat? I hope so. Memory is a lot. I'm just trying to make sure we're going through each step. How is memory managed? It's done both with hardware and software. The hardware is for speed, the software is for the flexibility. So this is something that both operating system writers and hardware engineers had to agree upon in order to get this to work correctly. So treat main memory like a cache, misses go to disk. How do we minimize disk access? Well, you can buy lots of memory, right? Exploit temporal locality. So so think of it now that your main memory is a cache, because you're trying to map all these processes, because you might have 120, process 120 as well, and where is he mapping to? You have all these processes. They might be in memory, they might be on disk. Exploit temporal locality. So usually you want to do fully associative if you can. How big should your block be? Because your processes are going to be in blocks, and you want to know where to map which one, and then write back or write through. These are all the same questions. Let me see if I can get a good picture to make this make more sense. Not quite. All right. In main virtual memory, each of your blocks are called pages. This is just like your cache lines with your cache blocks, except now we're calling them pages. Virtual address, it's your virtual number followed by your page offset. Notice it's 32 bits. So if your program has a 32-bit address, the first certain number of bits is the virtual number, and the rest is your page offset or your block offset. Misses, of course, are called page faults, and that's handled through an exception that usually goes to a routine in the operating system. Excuse me. routine in the operating system, which loads it from disk. But we want to be able to cache all these numbers. So, okay, here's another picture. Let's see. Page table contains address translation of the program. Your virtual addresses that might be coming from a program will then be translated to either a physical address or to a disk access. Page table. You have your reference, which goes into which page number it is. Page offsets is going to be forwarded along, and then after you get into this table, there'll be the physical page number, and this will give you your final actual address. Let's run that again. So if you have your full address up here, let's go give an example. 0xFFAC page offset is 38. Your final virtual one, just say for the sake of argument that this maps to right here, which has the number 004A. Your final one would be 004A 38. You okay, Matt? What is it, Matt? Tell me, Matt.
I just love page tables.
Oh, here. They did an example for me. We good? If it's a disk, then it's an exception. Stop the process, pick a page to replace, write the data back, get a reference page, update the page table, reschedule the process. In other words, it takes a very long time. How do we find it on disk? That is not for architects. We don't care. The operating system is what handles that. Windows has a swap file. Linux has a separate partition. So we don't care. That's an OS question, which Lynn, you can ask Lynn later on, since he's teaching it, not me. What's the size of this page table? Well, for MIPS, you have 32 bits. If the machine can support 1 gigabytes or 1 to a 30th of physical memory, we can use a page table size of 4 kilobytes to the 12th. Then the physical page number is 30 minus 12, which is 18 bits, plus another valid bit or other stuff, read-only, dirty. We'll say 3 bytes. How many entries is in the page table? MIPS is 32. You got a 2-bit page offset, because we're using 4 kilobytes, to the 20 or 1 million entries. So the total size of the page table to the 20 times 18 bits, which is about 3 megs. Still a little big, but that would fit in memory, so that's doable. So in this example, they keep the 3 megs of memory. How can you organize it? You can make it one continuous 3 megabyte region of physical memory. All right. You could hash a function instead of using an array. It's slower but less memory, aka if you want to use only half a meg, you would use a hash function to map to that page table. Or what's usually done is you page the page table. So you have a super page table which goes into a second, maybe a third page table as well. So you have your page offset, your virtual page, and your virtual super page. What does this look like?
TLB.
TLB, right. But what does it look like previous?
Oh.
So instead of page offset, we had block offset.
Yeah.
And then instead of virtual page, we had, it was the set.
The set.
Yeah, and then you have your super page. So it's going to be a little similar, but not exactly. All right. Are we going to actually see pictures? No, we don't. Curses. All right. How does this all work? You load your program to memory. You ask the OS to create a new process, construct a page table, mark all page tables invalid with a pointer to the disk. That is point. Then you run the program and you get an immediate page fault on the first instruction. Yes, that's what your processes do. First time it loads, there's an immediate page fault. That's just how the operating system handles it. And then it goes and starts loading it in. So how do we do a replacement? Well, how do we implement LRU? True LRU is expensive, but you can use heuristics. which is fine. Usually they have a reference bit that's cleared occasionally by the OS, and then pick any unreferenced bit to evict. You just choose something that's fast, and we found that that's usually perfectly fine. The issue is trying to translate the virtual address into a physical address, but to do that we have to first access the page table in memory, which means every time you did a load you have to go to memory to get the physical address, and then you could actually do your load, which is not good. So what do we do here? All right.
Cache it.
Yeah, you cache it, which we use a not TLC. I like that. That was good. That was good. I like TLB. All right, translation look aside buffer. We fix this by avoiding main memory in the translation. We buffer the common translations in a TLB. It's a fast cache dedicated to storing small subset of valid virtual to pointer translations. It's actually a very simple one. You get your virtual page and your page offset. That goes into your TLB, basically your tag, and then it pops out. You usually put the TLB lookup in the pipeline after the virtual address is calculated, but before the memory reference is performed. Okay, you can do this here. This may be before or during the data cache access. Without the TLB, we need to perform the translation during the memory stage of the pipeline, right? You could, I'm sorry. All right, other things, find, was a page data location, access permissions are usually stored inside the TLB just to make this a little more efficient. Let's see, gathering access, yeah, what's dirty, and what do you have permission to read and write? In your virtual memory system, it's not your virtual machine, but virtual memory is what we're talking about here. So notice you now have virtual and physical addresses. Which addresses should be used to access the data cache? Now think about that, because we could just cache the virtual addresses, right? That are inside the program, and then just use those, and then when you switch a process, just tell the cache to flush, and we're good to go. Well, virtual address, before VM translation, is it faster access if we use virtual addresses in our dcache? Now let's see if you've been paying attention.
Yeah.
Yeah, because you don't have to do the translation. Is it more complex though?
You got another level of what do you call it?
Indirection?
Indirection. There it is.
Yeah, the more complex is when you do a context switch, you got to flush that cache or do something. If you do a physical access, you have a bit of a slower access, but the rest of the memory system is stays the same. You haven't touched it or done anything with it. We just did that slide. We did that slide too. Hey, we're going to do them all again? Am I not going forward? Okay.
They all look alike.
Yeah, they all look alike now. All right, physical address cache to perform the TLB before cache. So you can use bits of the physical for the set. I just said all this. All right. Okay, so you have your virtual address, usually goes into a TLB, which then produces the actual physical address, which then goes into your cache, and then you can read and write. Notice that there might be some associativity associated with it. So that's putting it all together. It's a lot of caching, right? It's a lot of caching. Perform the TLB lookup at the same time as the cache tag compare. Okay. You can do this as well. You might have some aliasing problem. Two processes refer to the same physical location with different virtual addresses. And then when switching TLB may be invalidated. All right.
Oh, my bad.
Okay. All right, that was just a picture of the previous. Great. The support for virtual memory. The operating system does have to support some, and the reason for this is that when there is a fault like to access something that's outside of their process, which they can try and do, you need to be able to jump into the kernel or the operating system, and which is an executive, supervisor, or kernel level permission, and one that has user permissions. Namely, you have your user programs that are the normally running programs, and then if you need to manipulate with all the kernel structures, aka the page table, you need to be able to switch to a super user mode, supervisor or executive mode. Okay, does this go through? Oh, good. All right. We're going to go ahead and say loading a program into memory. So you have some disk pages. I'm okay with background noise, background music. Disk pages. We'll say the program's loaded over here, has some memory references. We want to load it in. Step 1, read the executable header and initialize the page table. Page table, we got nothing right now. And memory is reserved. Reference to 0, it's not in the TLB, so that's a miss. Go into the page table. If page table says it's on disk 1000, aka this piece of text, because we're trying to read the first instruction. Now we can update our page table. That's memory 1, not memory 0, but memory 1 as text 1, and the TLB says, look, we know that if you start with these addresses, it's memory 1, so we can just translate there. All right, fix that page fault. That's what happens when your program's first loaded in. Next, for 004, that's a hit to the TLB, and it just goes to memory. I'm not showing you your cache memory right now, just your virtual memory. So that's a hit, and we continue on. Next is 7FFC. We have nothing mapped to there. So memory could set it to zeros, and then we put that into the TLB. It's read-write because it's memory. It's not your instructions. It's actual data memory. Next instruction, 8, is read in, and then we have a reference to this guy, which is on the disk. So we have to load in M3. Notice that we had to evict someone, and in this case we evicted M2 because that's the least recently used. Notice our page table has M3 and has M1, but our TLB no longer does because the TLB is just caching the page table. Okay, any questions?
Go through it again one time.
Not a problem. Yeah, I know. It's hard to pay attention this long. Okay, we are loading a program and trying to run it. The program is located here. We have some text values, and it has a reference that 7FF is a reference to memory. It's probably doing a store, for example. All right, so we're going to load it in. Step 1, read the executable header and initialize. We're just going to say the first part of memory is reserved. This is common because that's where the kernel is. So the first one is in, first reference is probably to the first instruction, 000. The page table, which is in main memory, says it's on disk at level 1000, aka right over here. So when it goes into the TLB to ask for 000, that's a miss. So it has to, and that has to go to main memory, find out it's on disk. So then it has to load that text into main memory, and then we in our page table say it's memory location 1 or memory block or page 1. Sorry, memory block, memory page 1. There we go. We put that in our TLB as well because we just referenced that. Okay, that was the first instruction. I don't know, maybe it did an add or something. The next instruction, 004, it's a hit because it's in there. So it just went to main memory, read it, and we were done. It probably also went to a cache, which I'm not showing. I'm just showing memory.
And it's a hit because
it's already in the TLB. Because you got the 000 up here, 2 entry to memory 1. Excuse me. 7FF, that is not in the TLB. Page table, there is no map, which means it's not on the disk. We just need to allocate memory for it. So we're going to say it's this block over here. Memory 2 starts with a 7. It's read-write, so we should be good to go. 8 is still a hit because it's still within the TLB, because remember this TLB is really just caching that 0, and the next 3 are the offset. So it knows to go to memory 1 and then offset by 8. So it's a hit, it reads it in. The 2100 is a miss, so it evicts Well, it finds in the page table, oh, it's on disk, so it goes to disk, some iStatic, loads that into memory, memory 3 right here, and then updates the TLB.
Okay. Yeah, that's much better.
Much better? All right. Okay, multiple processes. Virtual memory is very good for supporting multiple processes, but you want to keep your mind, you probably need to flush the cache in between a context switch in case you have virtual memory that's still in there. Usually use a process ID to know which part of the tag or which piece of memory belongs to which process. Multiple processors, you can run 2 programs at the same time. Each process has its own cache. Why is that? Because area-wise, it's a lot faster. Processors have its own cache. May or may not share data. Code sharing is not a problem if it's read-only because you just read from DLLs, we're good to go. Sharing data is a problem because what if one processor has something cached that it needs to write to another? Okay, that's a whole new can of worms called Snoopy caches, which we're going to talk about next time. And that's it. That's it. Any questions? Yep, I know.
Turns out my brain actually clocks out around 3:30 p.m.
All right, great.